Spacetime is not an idea that was introduced by Einstein. It was introduced by several earlier scientists, notably Heaviside and Lorentz. The equations of special relativity may be thought to be the Heaviside equations of classical electrodynamics, written down around the time that Einstein was born in 1879. Einstein's contribution to special relativity was to put the finishing touches to the work of those who had gone before him. The big problem is that Einstein has been elevated into a cult figure, and this process has led to a corruption of the scientific enlightenment. The tendency is to take an equation by Einstein and try to prove endlessly and without purpose that that equation must be correct to ever greater precision, instead of finding the flaws in Einstein's work and constructively correcting them, as in this paper. The contributions made by Einstein in 1905 were to propose that the speed of light is the same in a frame that moves at constant velocity with respect to another, and to propose effectively that the Lorentz transform applies to classical dynamics as well as to classical electrodynamics. This was therefore an early unified field theory, giving a unified view of part of classical dynamics and of electrodynamics. Later, Einstein also proposed that there exists a relativistic linear momentum. This is the idea that actually leads to his famous rest energy equation, that rest energy is mass multiplied by the square of the speed of light. Around the same time, Minkowski spacetime was developed, a concept which simplifies the equations of special relativity. Horst Eckert has recently uncovered several flaws in Einstein's interpretation of his own equations of special relativity. The ideas by Eckert are correct, but the less enlightened part of the contemporary academic world is so ossified that it refuses to countenance that Einstein could make mistakes. Einstein himself admitted frequently that he could make mistakes and frequently corrected them in his papers. Minkowski spacetime is frequently known as flat spacetime, and this idea suggests automatically that there can exist spacetimes that are not flat. These are the spacetimes of general relativity, in which physics is thought to be governed by geometry again. This time, though, the equations based on this notion must be such that they can describe all of dynamics, now known as relativistic dynamics instead of classical dynamics. Specifically, the notion of acceleration of one frame with respect to another has to be incorporated into relativistic dynamics, because in special relativity a frame moves with a uniform velocity with respect to another and does not accelerate. Einstein's primary contribution, and the only one that has lasted the test of about 90 years of science history, is that general relativity can be based on geometry. This means that tensor equations retain their format in any frame of reference. That is, in a frame that moves in any way with respect to another. This is known as the principle of covariance. It was applied originally by Einstein to dynamics, but not to electrodynamics, introducing a basic schism in physics. This schism has only recently been bridged by the emergence in 2003 of Einstein-Kaplan-Evans ECE unified field theory, in which all the equations and laws of physics are generally covariant. This means that they retain their format in a frame of reference moving arbitrarily with respect to another. The problem faced by Einstein and his contemporaries was what geometry to use. Minkowski geometry was known to them as being flat spacetime, so what represents non-flat spacetime? This question may seem bizarre to the uninitiated, but it is designed to find what represents acceleration in general relativity, a subject which is itself designed to ensure complete objectivity in physics. Complete objectivity is the Baconian ideal. The description of nature must be free from any anthropomorphic influence, and that description is not thereby an idol of the cave. In the early 19th century, Riemann had proposed the geometry that was ultimately used by Einstein, having been introduced to it by mathematicians. In Riemann's geometry, two fundamental tensors are used to describe the way in which any geometry departs from the flat geometry of Minkowski. The latter is in itself a unification of the flat geometry of Euclid merged with time. These fundamental tensors are torsion and curvature. Einstein began to go wrong in several ways. The fatal mistake made by Einstein and all his contemporaries was to throw out the Riemannian torsion. This has led to a catastrophic corruption of the Enlightenment because the error has been repeated in academic physics, the optimistically named Standard Model physics, for more than 100 years. The torsion and curvature tensors are defined by the action of an object known as the commutator of covariant derivatives on any kind of tensor in any kind of space and any dimension. General relativity is restricted to four-dimensional spacetime. The commutator is an operator, meaning that it must act on a tensor. It is sufficient to consider the commutator acting on a vector in 4 dimensions. The commutator is associated with two indices denoted as subscripts. When these indices are interchanged, the commutator changes sign. When the indices are the same, the commutator is zero. It vanishes and in mathematical parlance is said to be a null operator. The latter acts on the 4-vector to produce zero torsion and zero curvature. When the two indices of the commutator are different, the commutator acts on the vector to produce both non-zero torsion and non-zero curvature. The structure of the defining equation is such that the torsion and curvature must both be non-zero. The key point is that it is not possible to assert or claim illogically that there can be a non-zero curvature and a zero torsion. Unfortunately, this is the error committed by Einstein and his contemporaries and repeated until the emergence of ECE theory in 2003. The error made by those contemporaries of Einstein now appears to be so glaring that one wonders why it was ever made. The error amounts to the incorrect assertion that there can be a non-zero commutator with equal indices. It is as simple as that. The only possible type of non-zero commutator must have indices that are different, and it must change sign when the indices are switched. It is said to be anti-symmetric in its indices. This error committed by the contemporaries of Einstein generates many sequential errors as shown in the sections of this paper, UFT 139, and a combination of all of them makes the Einstein theory completely unworkable and obsolete.